porque pelo menos metade do curso vai ser dado por Wendelin Werner em inglês, e monitoria também vai acontecer em inglês. Monitores ainda não chegaram hoje no IMPA, mas eu queria saber se, pelo menos nessa parte, todo mundo entende português ou não, ou eu preciso mudar para... Okay, so I think the question is if everybody understands English. So okay, maybe then I start in English, and so first of all about this course. So this course is in certain form a complicated course because it involves a lot of material in order to understand where we want to come. So it involves prerequisites are some basic of complex analysis and culminating in Riemann's mapping theorem, and then some knowledge of stochastic calculus and applications of Ito's formula. So I'm not going to talk about this, or at least I will mention some important things about this, and this everything will be included in exercise classes, which will be mixture of exercise classes with some extra lectures. So we will be working more or less in the following regime. So every morning, or at least maybe we will have more classes than it's scheduled if everyone has time. And every morning I will be giving part of theory, and then in afternoons we will have between 3 and 5:30 classes which are run by myself, Pierre Nolin, and Christophe Gorbin. And during these classes, we together will give some extra lectures on complex analysis, which is necessary, and also stochastic calculus, which will be used, and also it will be combined with exercises. So this will be important part of the course. Now, course itself has 2 parts, and the first part, which for most of you, as I see now, is going to be essentially trivial, but maybe not for everybody. So it's some short view on classical percolation, but with the idea that I will be giving only proofs of theorems which will be heavily used afterwards in more advanced part. And all this course is about what happens at critical point for critical systems. So in order to explain what I mean by critical systems and what is stochastic structure, the stochastic geometry of critical systems, so we need to go through some basic definitions. And today I will try to, through this lecture, more or less localize some important definitions, and which we will be using. So, but in order to have an idea, so first 2 lectures, or even 3 lectures, will be classical percolations. I will prove Menchukov's theorem and uniqueness of infinite cluster in both supercritical and subcritical regime. And then I will be approaching actually critical point. And the first important step, which is classical step, I will be proving all types and variety of Russo-Seymour and Welsh estimates, and I will prove them in 2 ways. In classical one, which is more intuitive, and then shorter one, which was given recently by Stas Smirnov. And then I will end first part by proving Smirnov's Cardy formula for triangular lattice. And then my part will finish with introducing Stochastic Loewner Evolution. And then Professor Werner will start at this point, and will go on conformally invariant models and what are last achievements. So in order to now start all this course, let me begin with formal definitions, which I believe most of you already know. I forgot to say, so literature which will be used, so of course books. First it's Jeffrey Grimmett, Percolation. It's second edition. Springer. 1999. There is more recent book by Bolobas and Riordan, also called Percolation, which is by Cambridge, 2006. Then I will follow also several lecture notes by Wendelin Werner. So first is random planar curves. And Schramm-Loewner Evolution. So this is already a book published by Springer, but you can find on archive. Second, it's also soon will be a book, lectures on two-dimensional critical percolation. It is also an archive, and it was a course given in Park City a year ago. And the third book is soon will be published. Also, it's in French. It's lecture notes by Wendelin, Percolation, a modèle d'Ising. So we will print all this material for you. So I just checked how many people are around, and then one extra what we will be using. It's also a recent article by Pierre Nolan, Near Critical Percolation. It's an archive as well. So that's essentially all literature, and then, of course, as I mentioned, we will be using some books on complex analysis and stochastic integration, but that's most of you already know. So these are canonical books. And okay, so let me start. First part, you may think that it has its own subtitle, which is called Stochastic Structure of Critical Systems. And what means stochastic structure? So models itself are rather simple. So let me start with Bernoulli Percolation. So this model was introduced in late 50s by Brodmann and Hammersley. So take your favorite graph, so G, which is set of vertices and edges. And then for essentially for most part of the course, graph will be triangular lattice. Though all theory somehow historically was developed on ZD. So other examples could be ZD, could be hexagonal lattice. And of course, you may think of many others, and also trees, etc., etc. So, but key part, because of recent progress of studies at critical point, is available only on triangular lattice. So many tricks, many arguments actually are developed for triangular lattice. So I will be somehow focusing on Z2 sometimes, and sometimes on triangular lattice. And classical theorems nowadays are available for broad variety of graphs. So it's actually theorems may change from graph to graph, but most of them keep the same structure. So let me define model. So we may have two types of percolation models, side and bond percolation. And let me start with side percolation. So for any vertex, how I will construct the model for every x which is belonging to vertex set of the graph, I will associate random variable, which is Bernoulli random variable, omega of x, which takes two values, 0 or 1. And when it takes value 0, I will say that vertex is open, closed. And when it takes value 1, I will say it's open. Okay. And then I want that this happens with probability p, and this is with probability 1 minus p. So probability, I don't know, omega x equals to 1 is p, and probability with small p, omega x equals to 0 is 1 minus p. And this I do independently for every vertex on the lattice. So I have at the end product measure. So I can introduce a configuration space. So all omega x's. So it's, let me put it like this, 0, 1. To, if I speak about vertices, and analogously would be if I talk about edges. So this is set of all possible configurations, and then I take measure p on omega, again with subindex p. It's simply product of, I use this notation, p. So this somehow overall axis in V. So this justifies name of Bernoulli Percolation. So model itself is simple. Question is which question, what you are going to ask, and then let me show you where we are heading. And this is not that. So here. So this is nice applet produced by Professor Gonsalves from Buffalo University. So you see here a square 100 by 100, and blue color denotes open vertex, and white invisible disks denote closed. So you see, for example, if I take box 18 by 18, that's a picture when probability p of being open is 0.6. So as you see, everything is encoded in this p, in image which you see, and all, of course, your intuition is producing for you right images. When you think of p being small, so you have very few. If I decrease still more p, less and less blue spots, and then you have very simple picture. Then, if I start to increase p, number of blue points will increase, and then it goes, and now picture gets more complicated, but still what you see is somehow is almost obvious. So every single point mostly is isolated from another point. Sometimes you have double, triple points nearby, and then question is if this picture is simple or non-simple depends, of course, on which questions you are asking. So first thing which is convenient to introduce as a tool is a coupling of all models as under one picture. So as you can see, if p is changing, this image is changing, and then it's convenient to think about all of them constructed in certain order that you can compare behavior for different p's. So coupling of all models. So if you want to construct now this percolation model for parameter p, we can behave in the following way. Take a uniform random variable, associated with vertex x, and then we will do the following. I take a unit interval, and then I want to construct percolation model with parameter p. So I fix number p, and then I look at the value of this uniform random variable. So it's uniform at 0, 1. Okay, and then if value is in between 0 and p, I will say that vertex x is open, and then you see that probability that uniform random variable stays in between 0 and p is exactly p. So I recover this expression. So now if value of random variable is in between p and 1, then I proclaim vertex is closed, and it's exactly probability 1 minus p. But what is convenient in this representation, that if you consider two models with two parameters p and p prime, suppose p prime is larger than p, you would like to construct representation in such a way that every time when vertex is open in the model with parameter p, it's also open in the model with parameter p prime. So what you do is simply do the same realization of x, and then what happens, you just mark point p prime. So now, if you want to construct model with parameter p, it's exactly what I just said. You look if value is between 0 and p, and it's the same for model with p prime. So if value of random variable x is in between 0 and p prime, then it's open in model p prime. But if value is in between p and p prime, what is going to happen, that it's closed in model p, but already open in p prime, and by this simple trick you obtain coupling of all models, such that you make realization of one random variable, and then you can construct any number of percolation processes such a way that they're ordered in natural way. Okay? So in this picture exactly you see this representation. So whenever I move this bar, which controls parameter p, then extra points are appearing. So now we go back to main questions, and questions in all these stochastic prots are questions of connectivity. So since this model originally was designed to somehow mimic behavior of fluid in sort of random media, so first question you would like to ask, how is structure of these of open channels, and now connectivity could be defined in various ways, and let us go and define connectivity. So we will say that 2 points are connected is simply x and y are connected. If there exists a path, so if I take, say, a square lattice, this what you see image is exactly on square lattice. And now if I have two vertices, x and y, which are on this lattice, so I will say that they are connected. If there exists an open path from x to y, and open path is alternating sequence of edges E1, then vertices x1, E2, x2, E3, etc., such that each x on this way is open, and they are nearest neighbor on your graph. Okay, so this defines connectivity. So I will denote that if exists an open path pi, which connects connects x to y. And I will denote this x is connected to y by path pi. Okay? So immediately you can ask question, what is the set of all vertices which are connected to x? And then we can define Cx. It's open cluster of vertex x is set of all y's such that y is connected to x. And now when you see image, whenever you look at this picture, no. So as you see in this sort of simple case, when P is very small, connected components are rather simple. So your eye, you can identify all of them by naked eye. So, and as you see, somehow most of them are just single vertices. Open cluster of this point is just itself, but then eventually you find some bigger ones. And again, as you see, this group, for example, this 4 and these 3 are not connected because this vertex is missing. So in order to go from this to that, you would need to cross diagonal. This is not allowed, so this is not a connected component. And then you want to know what you can say about typical behavior of connected component. And then again, when P is very small, everything is simple. But then if I increase P, picture gets richer. Now already you are essentially losing kind of image given by, but if you move around, you see, I don't know if it's visible, so connected component is red. So some of them are larger, some of them are smaller. Okay, but still, if I move pointer here around, you see that essentially even picture is getting more blue. Parameter is right here, 0.34. It's already, but still each connected component continues to be rather small. So if we increase density, so picture is getting even more blue. But still, if I move, not much changed. It's more difficult to identify from far, but still these components are not growing terribly fast with increasing parameter P. And this continues even now you have more than half of sides blue, but still if I move around, you see some of them are getting longer, but still kind of you have a feeling that there is typical behavior of these components. And then of course natural question to ask, what is typical size or what is mean size of this connected component? And then situation starts to get more complicated when I move forward. And now one of questions which is reflecting this behavior, you may ask question, whether do you have a path from left boundary of this box to its right boundary? It's one of canonical questions which was asked before, at the very beginning of the story. And then we are looking for the event if I take a box, a large box n by n, and in this case what you see on the picture is 100 by 100, and then you are asking if exists a path connecting left boundary to right, and analogously you can ask about vertical crossing, and then you would like to know how behaves probability of this event. So what can you say about this quantity? So what happens that if I move P, you see that typical size of the cluster is increasing. So one big component is starting to grow, but still there is no path connecting left boundary to right boundary. And then if we increase more, it grows. So you see this component is taking more space, but still around are spread typical clusters. And we can increase it until moment when, so in this picture it's top-bottom crossing. We can go to horizontal. So you see at this picture what you just see, if I close this, you don't have horizontal crossing, but you already appeared vertical crossing. And if I look for horizontal, I still need to move. Of course, it's symmetric, and then you see it happen. So what this picture teaches us. So from one side, when you ask this question about existence of horizontal crossing, and when P is very small, it just doesn't exist. It doesn't exist, and you push P higher and higher and higher, it keeps not existing, and then all of a sudden there is some value when you see it appearing. But what you see from this picture, that it doesn't appear as very tiny paths. When it doesn't exist, it doesn't exist, but once it appears, it's already a rather big aggregate, which is taking quite a bit of space, and that's part of phenomena which actually in infinite volume is transformed in existence of infinite clusters. So let me go to this a little bit later. So, and then if I would push P still higher, you see this connected component is taking more and more space, and then of course again when P approaches 1, again you go in some sort of trivial regime that everything is open, and essentially most of points in your box belong to infinite cluster. But even looking at this picture, there are many questions which are highly non-trivial. Of course, from one side, if I look at this, I see that now I have many crossings, because simply you have all these points on the boundary which are red. Just by default, each of them is connected to each point on right boundary, right? So I have lots of crossing. But actually, this picture still hides from you how this crossing is moving. You don't know geometry of the crossing. So, for example, if you start from this point here, and you want to appear in at this point here, so question is, how straight can you go in this green island? Do you do a lot of wiggly paths? What is connectivity of this object? So all these questions are highly non-trivial, but still they belong to what we would call today in this course classical part of percolation theory. So let me go back to critical value, and this is side percolation on Z2, and then you see this picture reflects something that happens around point 58. So when I cross next step, it appears, and that's exactly approximate value of critical value of P for side percolation. But now let me define it precisely what I'm talking about. So now, if you extend this image from finite box to infinite volume, you can ask how behaves cluster of the origin. So, open cluster of the origin. Of course, it could be finite, it could be infinite for some realization, and then one of the most fundamental quantities in percolation theory, theta P, is probability that cluster of the origin is infinite. Okay. So, of course, picture when P is very small suggests you that you have very little chance in this situation to produce configuration just throwing thousands and thousands times opening sites with probability P to obtain infinite open cluster. So it's very likely that probability that theta p equals to 0 for p small. And then maybe there is a hope that theta p is positive when p grows to 1. And of course, immediately when geometry is absent, so if you think about case of dimension 1, then there is no non-trivial phenomenon. In dimension 1, theta p equals to 0 for any value of p except 1. So there is no interesting happens. But now if dimension d is bigger or equal than 2, then you may ask if exists some value of p such that this probability becomes positive. And then you can formally define PC as infimum all p's such that theta p is positive. And now question is if this PC is non-trivial. Okay? If it could be strictly smaller than 1. Because of course if it is 1, then you get what you want. And fundamental for percolation theory, that if you look at, say, now when I say about D here, I think about a hypercubic d-dimensional lattice. It's fundamental that PC of dimension 2 is strictly smaller than 1. It's not very difficult. I will show that PC is strictly positive. This is nearly trivial fact. And it's nice Peierls argument to show that PC is strictly smaller than 1. So in this picture, once you move again back to criticality, now you see appearing this object, and this is somehow a central object of all these cores. So once you see this aggregate, you may ask questions. So what happens when you approach PC from the left or from the right? So once you are below PC, all your clusters in space look like finite, so just by definition of PC, and then you want to know how they behave. So you see, it might be already large, so I want to move one step. So you can get exceptionally large pieces, but then the rest is smaller. But this, what you see, of course, on this picture, is a finite box effect. And then if you approach from above PC, you already have infinite cluster, but this infinite cluster gets in some way thinner and thinner and thinner. And then you want to know what you can say about this behavior. In fact, this is the one of central topics of the course, to establish behavior of systems at criticality. And as you can see immediately, if we go to close to critical point, this object is extremely tortuous. And question is, how can you describe? And that is one of most remarkable achievements in recent years in probability theory, that in fact scaling limit of this object could be identified. So it was first step in this direction was achieved in 1999 when Oded Schramm introduced what he called stochastic Loewner Evolution. And this process, in fact, by Oded was introduced in context of self-avoiding, loop-erased random walks. And then soon it was realized that this object, or actually family of these objects, are suitable objects to describe curves at criticality. So as you already, most of you are familiar with these pictures, so I show some simulations done by Van Sambe for us. So this is exactly curve described by SLE with parameter 6 on triangular lattice. So this is exactly limit critical cluster. So now when we speak about critical cluster, then of course natural question which you ask is, so what you can say about infinite cluster? So a critical cluster, is it finite or infinite, first of all? So what you see in scaling limit. And then question is how this function behaves at critical points. So this is another fundamental question in percolation theory. Continuity of theta p at PC. So it's very easy to see that, of course, theta p is equals to 0 below PC, just by definition, and then it is continuous when p is strictly larger than p. An expected shape of this curve is between 0 and 1, 0 and 1. So here is PC. So it is 0 below PC, and then it starts at PC and goes to 1. And then, of course, once you are again in a regime which is nearly trivial close to 1, you have a lot of properties of this curve. But question is, what happens around this point here, around PC? Can you continue here or not? And what is known today, that this is theta at PC equals to 0 for d equals to 2 and d equals 19 and more. So this is one of the crowning results of percolation theory, which was proven by Kesten in 1980. And this result is by Hara and Slade, was proven by using laser expansion techniques in between late 80s and beginning of 90s. So in between dimension 3 and 18, it's still open problem. So it is believed widely in community that laser expansion technique should work until dimension 6, but it's not really done. And dimension 3, 4, and 5 are still waiting their own methods. So now, going back to our model, so triangular lattice also belongs to this company of lucky graphs where we know. So it was immediately extended by John Weerman. Proof of Kesten was done originally for Z2, and this is also correct for triangular lattice. Okay, much of story of percolation on ZD was in fact done also for bond percolation, not only side percolation. So instead of now taking variables 0 or 1 on vertices, you can replace and take another space which is edges and take 0, 1 to the set of edges. And now each, instead of looking at vertices, you can think about edges being open or closed, and then now where I'm heading, it's a question of connectivity. So if you're now talking about percolation of edges, then we say that two edges are connected if they share a common vertex, and then if you have open path, means you are moving along edges of your graph, and all these edges supposed to be open. So question is how these two processes are related, side percolation or edge percolation. They are, of course, very similar. And in some sense, side percolation is, if I could say, a little bit abusing notations. Side percolation is more general. So each edge percolation could be mapped on side. But one has to be careful when I say mapped. So if you look at your graph and then you are studying edge percolation, right? Then say think about Z2. Then I can construct graph where percolation on edge percolation on Z2 will be represented by side percolation on new graph. And how do? You simply, with each edge, you construct you associate new sides. So let me put it in, say, in red. So with each edge, I will associate side. Okay. So if you now have Z2, this is your original graph where you're studying bond or edge percolation. Then I will construct new graph, just simply associating with each edge a vertex, right? And then I will declare naturally that vertex is open if and only if edge is open. But question becomes, what is about connectivity, right? And then edges are connected if and only if corresponding vertices, two new vertices are connected if corresponding edges have common vertex, right? So now you see that these two edges, two vertices are connected, and these two are connected, and these two are connected, 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 connected. But also these two vertices now are connected because edge corresponding to this vertex is sharing common vertex on original lattice Z2 with this. So this is also present, and this is also present. So you see that what is now born in this picture is not anymore a planar graph. So if you would do it carefully all around, so you will get new graph which has edges of this type. And then you consider side percolation on this graph, and questions of connectivity of this graph are equivalent to edge percolation on this graph, on Z2 original. But it only in terms of connectivity. You cannot say that models are equivalent. What I am claiming that if you are searching for presence or absence of infinite open component on Z2 edge graph, this is equivalent to question of having open infinite component on this graph in side percolation. But generally, if you look for example, you may consider so-called AB percolation, when instead of looking pass 1, 1, 1, 1, which is all open, you can look for alternating pass 0, 1, 0, 1, 0, 1. And then immediately you can construct counterexample that edge percolation of this 0, 1, or sometimes called AB pass is not equivalent of presence of alternating pass on this graph. So one has to be careful about this representation. So, okay, so much of the story was developed on Z2 bond case. And it was celebrated result of, again, of Harry Kesten, that it was established that PC of Z2 bond case is 1/2. Okay. And for us, actually, during this course, is not going to be very important actual value of critical parameter. So it's only actually very few graphs which enjoy this fact that we can compute them explicitly. So again, it was proven. Proof of Harry Kesten was generalized by John Bierman to triangular lattice side case. So this we will be kind of remembering during our course, that PC side on triangular lattice also equals to 1/2. And then there are several other graphs where this quantity is known, like, for example, side percolation on hexagonal lattice. Okay, so this is more or less picture. So you see that we have this change of behavior at critical point, and what I was pointing out, that this critical phenomena is reflected by the fact that something happens very globally. So you don't have crossing, suddenly everything becomes connected. And then in infinite volume, this is reflected in appearance of infinite infinite cluster. So now you may ask various questions about these regimes, what happens, and then let me formulate sequence of theorems which we will prove quickly in next lectures. So behavior in subcritical regime, P is strictly smaller than PC, and then in this situation, first important statement is that almost surely all open clusters are finite. Almost surely. And then one of the fundamental theorems is that radius of this open cluster decays exponentially fast. So Menshikoff's theorem on exponential decay. So this theorem is very important not only because it gave conceptual tools, were introduced new tools how to deal with these models, but also it has an enormous amount of applications which also will be used in our course. Now, behavior in supercritical regime when P is larger than PC is of course characterized by presence of infinite cluster. So theta of P is strictly positive if P is bigger than PC, and then this is equivalent to the statement that infinite open cluster exists in your picture. Infinite open cluster exists almost surely. And then you want to know something about geometry of this infinite cluster, and also you want to know how many of these clusters are. And one of the key theorems for large class of graphs that once infinite cluster exists, it is unique. So this is true for ZD, is true for triangular lattice. However, if you think about phase transition, so if you look interval 0, 1, and you are taking graph, so it's not a priori obvious that this PC is unique in the following sense, that once P is below PC, no infinite cluster. It's a not very difficult statement to say that infinite cluster exists. But what is non-trivial to say if it's unique or not. And actually, we have examples of graphs such that you have two PCs, PC1 and PC2, such that the following happens. When P is very small, system is rather weak, so you have no infinite open cluster. Then, after crossing value PC1, infinite cluster is born, but your graph is so large that it has space to coexist infinitely many infinite clusters. So in this region, we have infinitely many infinite clusters. And then you are increasing P, so you have more blue points on your picture. And then there is next PC, such that suddenly all these infinitely many infinite clusters, which are getting bigger and bigger and bigger, they suddenly join to one, and from this point starts unique infinite cluster. So this phenomena was first observed by Newman and Grimet. And first example, to my knowledge, of a graph which has this behavior is 3. You can think of binary 3, times z. So you can think that you have binary tree which is multiplied by z, so there are infinitely many floors of this graph, so it's still tree-like. So it has enough space to accommodate infinitely many infinite clusters. And then when you increase, they merge at this point. So all graphs could be characterized by this property. Either you have a single phase transition that you have no infinite cluster and then suddenly you have unique infinite cluster, or you have no infinite cluster, infinitely many, and then again unique. And possibility to have multiple but still finite number of infinite clusters is ruled out. So there are no graphs which has this property that you have no, then finitely many, and then unique. So it's either 0, infinite, or 1. Okay? So this is very important phenomena which happens in supercritical regime. And again, this theorem will be fundamental to us, existence of uniqueness. So also I will give a very quick proof of this, of uniqueness. And then question is, again, so what happens when you approach PC? And then things getting complicated because theta of P, when P goes to PC from above, is converging to some value. We still don't know if it's 0. So, but even in case of Z2 or triangular lattice, when we already know that this is 0, we know continuity of theta P. Behavior of aggregate near criticality and at criticality largely is not known. But what I mean is not known for mathematicians, it's not rigorously established. Now, physicists through years had many tools and theories developed to target this problem. And then actually there are two essential tools, some sorts called scaling theories and renormalization tools. And all of them essentially are not rigorously established. So we do not have mathematically developed machinery to perform all calculations which physicists claim being right, and actually they achieve results which are supported by simulations and also by some more rigorous argument. However, mathematically, this machinery is extremely complicated. And then what physicists observe using all these arguments, that near criticality happens something which they call systems start to get universal. So behavior of these random objects suddenly becomes insensitive to original lattice structure. So it's not important if behind of this picture stays Z2 or triangular lattice or hexagonal lattice. Behavior of aggregate, the way it behaves, is somehow universal for many models. And that's one of the great mysteries. It's observed experimentally, and as you can think, if you think about matter atomic structure, because it's actually supposed to mimic phase transition, this phenomenon of universality somehow is not directly supporting atomic structure of matter. So it's kind of very interesting phenomena to be understood. So scaling theories, first of all, tells that when parameter P approaches PC, laws of certain quantities start to behave like polynomial. And then question is, how can you identify these exponents, and what can you say? And one example of such exponents could be crossing probabilities, which I mentioned before. So if you look at large box, and then again we ask the same question, what is probability that you have left-right crossing? Then the following happens. If we take this parameter P, which governs say, vertices to be open or closed. If P is below PC, this probability decays exponentially fast. So exponential decay if P is smaller than PC. And what I mean, of course, when you send this size of the box to infinity. Okay. Now, if P is bigger than PC and box is going to infinity, this crossing probability converges to 1. So this crossing somehow, if you start to enlarge this box, is appearing eventually as converging to 1 if P is larger than PC. And then it was conjectured by physicists that if P equals to PC, in particular case of two-dimensional lattices, it behaves like n to the power minus 5 divided by 48 plus some correcting term O small of 1. And it was first observed by using highly non-rigorous tools, then was improved by using methods, again, theoretical methods from quantum gravity. So it first was predicted by Duplantier, and then the first achievement in this direction was proof provided by Lawler, Schramm, and Werner that indeed this exponent is minus 5 of 48, and we are going to prove this exponent during this course. So you see, this connectivity starts to decay polynomially. So this already points that behavior of at criticality is changing drastically from subcritical. So actually, theta p is still 0. So infinite cluster doesn't exist, but infinite cluster behaves in completely different manner. So out of this, you can conclude that size, expected value of cluster, already is non-integrable. Object itself is finite, but expected radius of infinite cluster at critical point is infinite, and therefore you can think about this object as something huge aggregate, and then intuitively one could think at criticality that whenever you think size, somewhere in space you are seeing these clusters, and if you look at the picture from far and far and you look at boundaries of these clusters, so at criticality, if space were infinite, on this picture this huge red object would be almost surely finite. So if looking from far away, you would find its boundary, and then you check this boundary, you mark this boundary, and you start to look from even far. So eventually this object, which you just noticed as huge, is going to be getting smaller and smaller, but by that time you would discover even larger object which has exactly the same law of behavior of boundary as previous one. So if you are making this procedure, somehow you are looking at somehow scaling limit of these boundaries. And that's a remarkable achievement, that this behavior of this apparently completely undescribable curve actually is rather simple and could be given in simple terms. And this is given by Schramm-Loewner evolution. So already this fact that you can do this leads you to a lot of important consequences. In particular, you may think, okay, what your intuition tells you about structure of this object at criticality, how critical percolation is done. So as I just said, object is almost surely finite, but actually expected value is infinite. There are many theorems which are saying something that, like Kesten.s theorem, Harris-Kesten.s theorem, saying that if you take origin at criticality, then you will have infinitely many open and closed circuits, disjoint circuits surrounding this origin. So what is the picture actually at critical point? And using Schramm-Loewner's techniques, one can get some already glimpse on this geometry. So for example, if you think about picture here just below PC, so you see how these clusters are done. They are sort of one connected component is touching another connected component, and there is a lot of boundary. Observe this picture here and this picture. So two objects, even though they are disjoint, they are touching, their boundaries are touching boundary of each other in many places. So one of important consequence of technology which was developed with Stochastic Loewner Evolution is that you can compute what is so-called arm exponents. So, and one, I will give exact definitions a little later. So, but image which you have below critical point, you have many objects which are having this shape schematically, and you have many points which are close to each other. So it seems to you that a little bit more of P added, you will connect here, you will connect here, here, and here, and etc. is born critical cluster, which is still finite but has this shape. But this is wrong intuition. So critical cluster has rather different form. So a big cluster would have what I would call its body, and then has like satellite-looking antennas, and this happens to all scales. And then when you think, so this is one open object, and if you have another open object, it has the same shape, and one cluster touches each other only by the end of these tips of antennas. So it's not like these roundy nice things are touching each other. So clusters have this type of form, and in between them, and usually two big clusters will have no more than one touch, and in between will be smaller scales object, etc., etc. So you see, this is more intuitive picture just by obtained by using arm exponents, because if you would have pictures like that, it means that you have one open path here, one open path here, one open path here, one open path here, and there is also closed path here and closed path here. So it would be, if you can think from looking from very far in this region, you would find from this point one arm, another arm, third arm, fourth arm, fifth and sixth, and points which have outgoing 6 arms essentially are not existing in a small volume. So everything is quantified, and I will give these estimates. We will derive all these critical exponents, but such points simply do not have density at criticality. So critical cluster is looking like this object, and still many questions about geometry of these objects are open. And let me make break for 15 minutes because of changes of video, and then we continue in 15 minutes.